all, I would like to thank the organizers of the Trimester Program for giving me the opportunity to be here and to give a talk. And yes, so the talk is devoted to the analysis of the free boundary for the double obstacle problem in dimension 2. Now let me start with the setting of the problem. So we assume omega is a given set invariant, open boundary, with a given field that it has a smooth boundary. The analysis will be local. And
a little loud.
I'm sorry.
A little
Little
louder.
loud.
Little louder.
Yeah.
Speak a little louder.
Especially so long.
I will try to reach the maximum. So given two functions, π1 is equal to π2 in omega, they are called obstacles, corresponding to lower and upper. For now we can just think of them as continuous function. So the problem is to minimize the Dirichlet energy over omega of function u, where u is a function in w1 to omega, which is forced to stay between the given obstacles and omega, and it satisfies a given boundary condition. U is j on the boundary of omega, and the boundary condition has to satisfy the compatibility condition π2 greater than π1 and the omega. So the first question we would ask is the existence and uniqueness of the minimizer, and we can state that there exists a unique minimizer called the solution to the double obstacle problem. I will always use this abbreviation with π1, π2. The proof is standard and it follows the same lines as for the obstacle problem. And we can see that the problem turns into a single obstacle problem if we just take phi2 is plus infinity, if we think of phi2 as plus infinity. And the proof of existence and uniqueness of the minimizer follows the same. And we can also show that the minimizer satisfies the following variational inequalities. So u always stays between the obstacles by the assumption. So, and then we have that Laplacian u is in the set where u is greater than π1, and in the set u is less than π2. So here we want to say that u is a superharmonic function when it doesn't when it's above the lower obstacle, when it doesn't touch the lower obstacle, and it's a superharmonic function when it stays below the upper obstacle. And these inequalities can be obtained just by looking at the obstacle problem, because in this set u minus u solves the obstacle problem with minus phi2, and in this case we already have the classical single obstacle problem. And the second question, which comes right afterwards, what is the optimal regularity of the solutions? So, and it's known that if the obstacles y are C2 omega, then we can show that u is C11 locally in omega. And it's obvious, and as we know that C11 is the optimal regularity for the single obstacle problem, and this is therefore also the regularity for the double obstacle problem. And this result has been obtained in two papers. I can write the first one is by Anderson, Shahorian, it's a paper from 2012. And it's entitled Double Obstacle Problems with Obstacles Given by Known C2 Hamilton-Jacobi Equations. And also the regularity is derived from more general variations in context for more general results in a paper by Gohar and 2015. And the paper is entitled An Overview of Constrained Free Boundary Problems. So knowing the optimal regularity of the solutions, we can already move on to the analysis of the free boundary. So the free boundary.
Can you say that when U doesn't touch both of the obstacles, U is harmonic?
Yes, yeah, exactly. Yeah, I was just going to say that in a moment.
Sure, yeah.
Yeah, so as usually we denote omega U is the set where U doesn't touch any of the obstacles. So, and it's the non-coincidence set. And exactly in this set, U is harmonic. And also following the usual notations, we let gamma U to be the boundary of omega U in omega, called the free boundary. I will also make a few more notations. So for Ci, we will denote the set where U is the obstacle phi I. So the sets where U is touching, like here I is 1 and 2. So the set where U is touching the lower obstacle, or the set when it's touching the upper obstacle. And also I will denote by lambda the set where the obstacles touch. And for me, unfortunately, I call this coincidence set, and I realized that I shouldn't, because usually this is not what is denoted as a coincidence set, but unfortunately I did it, but I hope I will be forgiven for that. So now let me just try to see these sets on a picture. So we have a lower obstacle phi 1, and we have an upper obstacle phi 2. And then we have a solution. Can you think of solution of this one? And then the free boundary will be this set and this set. So we get two pieces of free boundary. So we will denote gamma 1, gamma I, the boundary of the set Ci in omega. And then we have gamma 1 here and gamma 2 here. So, and the free boundary gamma, by our definition, will be the union of gamma 1 and gamma 2. So if we look here at these three boundary points locally, our solution doesn't see the upper obstacle, right? So we are in the setting of a single obstacle problem. And the same here, if we look at this free boundary point at gamma 2, then locally our solution doesn't see the lower obstacle. So we can analyze it as in the single obstacle case. Here, what was more interesting to us was to look at this point where the obstacles touch itself. So this set, which we assume that it's not an empty set. So from now on, our analysis will be focused on this situation, when we have obstacles touching and we want to see how the free boundary looks locally at these points, at this set. And for this, I will start with an example, a motivated example. So we can just look at this function in our tool. You know this x1 squared signal x1 plus x2 squared signal x2. And if we draw the picture, it would look like this. U naught is, and the obstacles we can take. P1 is minus x1 squared minus x2 squared, and P2 is x1 squared plus x2 squared. So the lower obstacle and the upper obstacle, and they touch exactly at one point. So u is p1 here, u is p2 here, and u will be minus x1 squared plus x2 squared here, and x1 squared minus x2 squared here. So just let me say a few words about this example. This example I was given by my doctoral thesis advisor John Anderson at ETH, and he just gave me this example and asked me if I'm interested to investigate this object. And yeah, the answer was why not. And now I will try to say what has been obtained after that. It's really heavy. One has to be strong in Germany. Yeah. So just for the simplicity, we will study a normalized double obstacle problem. So now, from now on, all the discussion is in R2 only. Only in the end, if I have time, I will make some comments about higher dimensions. So we have a normalized double obstacle in R2 with polynomial obstacles. And the equation is the following. U is P1. There, lambda 1 is the function P1 is negative, and lambda 2 is the Laplacian of P2 is a positive constant. So the choice of the signs is clear. That's why we have the sign imposed. It follows from the variation inequality. So, and we also assume without loss of generality that 0 is a free boundary point which is both in gamma 1 and gamma 2. Exactly the type of point we had up there is a free boundary point, and we want to see what is happening locally at this point. And without loss of generality, we can assume that our solution and the gradient at the origin are vanishing, otherwise we can always subtract the first order polynomial, and then the same condition would be satisfied by the obstacles as well, because we know that the solution is squeezed between them, so it has no choice. And gradient P2, 0 is 0.
So the choices of P1 and P2 are no more this distant.
I'm coming to that.
No, I mean the choices there are very general. So that P1 is.
Polynomial.
So now there are polynomials in R2.
But they are very
And
general.
for now, yes, we have only these two assumptions.
Okay.
But we will see that, and we have this assumption. So we will think of P1 and P2 to be homogeneous second order polynomials. Because after the blow-up limit, we would get polynomial, second-order homogeneous polynomials. So initially we take them homogeneous of degree 2, just to simplify the case a bit.
So you allow them to touch in a long array of segments.
Well, so yeah, thank you for the question. Now I will make a comment about this, because if we allow P1 and P2 to touch on the line, then we will have only half-space solutions, and that will be similar to what we would get in the single obstacle problem. And the new result come actually in this case when they touch at a single point. I will just come to this now. All right. So now, under these assumptions, we can look at the rescale solutions. U1x is URx divided by R squared. And then we can say that the rescalings are uniformly bounded in R. And we can say that up to a subsequent, we can calculate limit U naught, we can think of C1 alpha locally. And U naught is called the blow-up solution. And we can use, we can apply Weiss monotonicity formula to show that U naught is a homogeneous global, not global, solution to the double obstacle problem with P1 and P2. So now once we know that the solutions are homogeneous in R2, we can easily classify them, and I think that will be the next step, classification of blow-ups. Blow-ups in R2. So first of all, I will give two definitions. First, we say that we assume that U is a global solution. We say that U is a half-space solution. With respect to P1 or P2, if U is I don't talk about it later. Sorry, I'm just say something first, but I can do it afterwards. U minus P1 is this form. Or P2 minus U is lambda 2 over 2 xe plus square, where E is a unit vector in R2. Yeah, so you may think why I am giving a definition of half-space solution if it's well known. Because I will need to say something about this a bit later. Because as we will see, if we just take this half-space solution corresponding to P1, it doesn't necessarily satisfy this assumption. So the half-space solutions for a single obstacle problem not always give a half-space solution for the double obstacle problem. And this will be another point of the classification of blow-ups, but an easier one. And we will also give a definition too. And the aim of this definition is to give a name to this object. So we say that U is a double cone solution. Problem. If this set C1 is equal to pi 1 and C2 is P2 are commons with a common vertex. Yeah, so if we go to the example above, then we see that C1 is this one and C2 is this one. So we get two cones which intersect at the origin, and in this case we see that the free boundary is a cross. So let me see. Now under the general assumptions, I will say what are the general assumptions on the obstacles P1 and P2, which I wanted to mention here. So P1 is an obstacle of this form. We can always think, I will say why we can take this simplifying assumption. And P2 is A2 x1 squared plus C2 x2 squared. Of course, when we have a homogeneous polynomials, then we should also have this term B x1 x2 and the same here. But we can always rotate the coordinate system and subtract harmonic polynomial and to cancel these terms out, because this will preserve the free boundary. So we can always do that. Yes, and the other assumption was that we assume that Laplacian of T1 is strictly negative. So we will have that A1 plus C1 is 0, and A2 plus C2 is less than 0, and A2 plus C3 is positive. And the other assumption we will make will be that A1 is less than A2, and C1 is less than C2. But these assumptions are entirely justified, because if any of these inequalities becomes equality, then we have only half-space solutions. So we don't have any this type of solutions. And since we are mostly interested in this object, since this is the new behavior, we make these assumptions just to simplify the discussion. Yeah. Now I will state the main theorem on classification of blow-ups. So let U0 be homogeneous, degree 2, global solution. That was the problem with P1 and P2. Then, so if U0 is not half space or polynomial solution, then it's a double cone solution. So this theorem entirely classified, because then we see that we have either solutions of this type, which we call double cone solutions, half-space solutions, and polynomial solutions, which means that we may not have solutions where we have more than these 4 cones. Now this theorem has some cases which made the problem a bit, which surprised me a bit by working on it. So case 1, if A1 plus C2 is 0 and A2 plus C1 is 0, then we have infinitely many rotationally invariant double cone solutions. So we basically get anything of these 4. So here we have this and something like this. Yeah. So this would be the set where U is P1. This would be, let's say, the set where U is P2. And we can see that this angle, which corresponds to these 2 other cones, which are the non-coincidence set, here we always have a right angle. But we can take basically any this kind of cones, and this will give us a double cone solution. So we can rotate it, and we have infinitely many possibilities. But there's also case 2, which is very different from case 1, that if A1 plus C2 and A2 plus C1 is negative, then only 4 double cone solutions. That means we don't have this situation anymore. We just get solutions of this type. Let's say this is the case. These are the non-coincidence sets, S1 and S2. These are the cons C1 and C2. So then we can really calculate what are those lines. And these lines cannot be just any line on the R2. And for this angle theta, this will be important later, we get this formula that cosine squared theta has to be A1 plus C2 A2 plus C1 divided by A1 plus C1. A2 plus C2. And this is a number between 0 and 1. Right? So now if we look at this expression, we see that if this is negative, then indeed this number is between 0 and 1. But when we look here, then we can already say that if this is positive, then this cosine square theta would give us something negative. Because we know that A1 plus C1 is negative and A2 plus C2 is positive. And that explains the case 3, that in case 3, which says that if we are neither case 1 nor case 2, then no double consolutions. Not 1 and 2, then no double consolutions. Yeah. So this is the
Do
class.
you mean the inequality is
Sorry?
converged? In case 2, you said that the product is negative and cosine square is positive.
Sorry? This is negative, this is negative. So we get a number between 0 and 1. Yeah, and then in case 3, this will be negative. So, and we don't have any double consolutions, and we cannot obtain any value for the number theta. And I will also mention one thing concerning half-space solutions, that in this case, we can take any half-space solution corresponding to P1 or P2, and it will be half-space solution for the double obstacle problem. We get infinitely many possibilities. In case 2, we have infinitely many possibilities for half-space solutions, but the free boundary gamma 1 or gamma 2 cannot be anything. It's forced to oscillate inside a given cone, which we can compute in terms of coefficients. So we get something also surprising for the half-space solutions, because not every direction on the plane R2 gives us a blow-up limit or gives us a solution. And in case 3, if we take A1 plus C2 is positive, A2 plus C1 is positive, then we get half-space solutions only with P1. Because if we take a half-space solution with P2, it will not stay above P1 everywhere. So this was another.
So you get half-space solutions when the two polynomials touch in half-space, basically. Is that the case? Or?
If the polynomials touch on the line, then we'll have only half-space solutions and polynomial solutions. So I'm not discussing that case. I'm discussing only the case where the polynomials touch at a single point.
But what then you say, then you're saying that you will have harmonic functions that are touching only at that point.
Yes, P1 and P2 touch only at 0, only at the origin.
Yes, but the solution, you said solution would be a polynomial solution.
Yes.
So is that going to be a harmonic polynomial?
So the solution can be either P1, P2, or it can be a harmonic homogeneous polynomial.
So it goes in between them.
Yeah.
Okay.
It cannot be another polynomial, because then
Okay.
it will convert it to the maximum principle. But here we are mostly interested in the double consolutions, so I'm not. I don't want to talk too much about the other solutions. Here I will just say that this theorem, the proof of this theorem, is very easy, long, and boring. And Eric can confirm it. He was forced to read it as my co-advisor. So therefore, I will not talk about the proof, just a small sketch. So if we think that the solution is not a half-space solution, that means it has to be, we need to have a harmonic polynomial in an angle, because we already know that the free boundary consists of lines, which has to touch the obstacles P1 and P2 in these two lines in a C11 way. And this, just knowing this, we can already see what will be the possibility, what would be the equations for these lines, what would be the value for the polynomial Q, and we can also compute what this angle is. So basically, the whole proof is only about working out this case, and seeing that when we start with this problem, then we get these three cases. And also here I want to make a short remark that just not to be very confusing here, we can write it, we can consider this polynomial, which we define as x1, x2 plus p2, x2, x1. So we switch the coordinates here for p2. And then we can say that in terms of this polynomial, if p is equivalently 0, we have infinitely many double cone solutions and half space solutions. If p changes the sign, then we have only finitely many double cone solutions, and if p has a sign, then we don't have any double cone solutions. And here also we get an interesting instability result, because if we take these polynomials, p1 is minus x1 squared minus x2 squared, exactly as in the picture, then we get infinitely many double cone solutions. But then if we take epsilon a very small number, and we take p1 to be the same, but just take p1 is the same, and p2 we take p2 epsilon as 1 plus epsilon x1 squared plus 1 plus epsilon x2 squared, then we can already see that for these two polynomials, there are no double cone solutions. So even though we change the obstacles just a little bit, but we get a totally different picture of the free boundary. And this was another interesting point which gave us some thoughts.
I mean, yes, there is of course, I would guess there is of course also the boring case that that the free boundary is only a point, right?
No.
No, that's not true.
No. So the free boundary is the union. So like if we look at this point, so here the coincidence set is lambda, where the obstacle touches a point. But the free boundary is this entire cross, gamma 1 with gamma 2. So the free boundary.
What I'm saying is, when you just take the harmonic, right? And you put one polynomial on top and one polynomial
So that's a
on
harmonic
bottom
case.
that can be factored.
Well, I don't study the harmonic case.
No, I just take as an example
Yeah.
a harmonic function
Yes.
and I touch it from above by a polynomial and from below by another polynomial.
Yes. Yeah, then the free boundary is a simple.
That's exactly
Is the point.
That's
Yeah.
exactly
Could
the
be.
solution.
Where was this excluded?
This is half spaces are polynomial solutions.
Or polynomials.
The polynomial
So we say
solutions
that
are
if
harmonic
U naught is
polynomials.
not a half space,
It could be that
Harmonic
case.
polynomials.
if it's not a half space or polynomial solution, then it has to be double cone
Yes,
solution.
exactly.
Yeah.
So
Just to say
polynomial
that we
solutions are
cover all
harmonic
the
polynomials.
class.
That's not excluded.
That's not excluded.
Okay, fine.
Yes. So now we can think that we are done with classification, and we can perhaps more interesting part, the uniqueness of blow-ups and regularity of the free boundary.
So this is two-dimensional, yeah?
Yes.
So, because in 3D,
Yeah, I want to come to the 3D, and I hope to get some advice or ideas.
it could go a lot there. Should have a training system.
So now we move on to the universal collapse and regularity of the boundary. I will need the classification here. Yeah. And the discussion is different in different cases, so I will start with case 1. And it's easy to see that case 1 is equivalent to just have obstacles P1 is minus x1 squared minus x2 squared, and P2 is x1 squared plus x2 squared. Because otherwise we can always subtract harmonic polynomials and divide the solution by a positive constant to achieve this. So we may always think that we are in this case. And now let us assume that Uj converges to some mu naught, which is a double cone solution in this case. And then we consider the sequence. So probably I went too fast. I need to give some motivation perhaps. So the proof is based on a linearization argument. And I will try to give a very, very short sketch of how the proof is carried out. And I think it follows the method linearization argument which has been used by many authors, and I will move on to how it's being done. So we assume that we have solutions to the general double obstacle problem with P1 and P2. Is any solution, Uj are any solutions, they don't have to be homogeneous, and we assume that they converge to a double cone solution. And then we consider the following sequence, Bjx, defined follows, Uj minus μj divided by Uj minus μj L2B2, where μj minimizes this node, Uj minus mu L2B2, where mu is any double cone solution. So in this linearization argument, we just choose a double cone solution which is the closest to Uj in the L2 node. And then we can show the following properties, that Vj is W12 locally is bounded, and therefore we can show that Vj converges to some function V0. Furthermore, we can show that this convergence holds locally in W12. And And these are obtained by standard arguments from the calculus of variations. And now let us see what do we know about V2, about the function in the limit. So if mu naught is this double cone solution we started with, so this is the set where mu naught is P1, this is the set where mu naught is P2, and these are the non-coincidence set. Then we get that V naught has to be 0 here, it has to be 0 here, and it's harmonic here. Besides, we know that it's a Sobolev function. And then we can see that each of these cones, S1 and S2, for V we have a following representations in polar coordinates. It can be written as the sum r power to k from 1 to infinity, ai k cosine 2k theta plus b I k sinus 2k theta, where I is 1 and 2. But then, after having this expansion, we can see that ai1 is bi1 is 0. And this we obtain simply because we chose mu j to be the minimizer of the norm of uj minus mu, which implies orthogonality, which implies that this V naught will be orthogonal to these functions cosinus to k theta, sinus to k theta. And then we see that once we have that ai1 and bi1 are 0, then we can see that the first term we have here is already of order R4. And this already gives us that for v naught sx L to b1 is less than equal s power 4 v naught L to b1. And this already looks like a flatness improvement regularity result. And let us see what it says in terms of our function uj. So basically what we can say now that if uj is close to a double convolution, if u is close to a double convolution, if u minus mu is small, then u minus mu1, where mu1 is the closest double convolution to u1, after the rescaling, is less than equal as u minus mu, the initial one, and plus some lower order terms, so we can write it small o u minus mu. And then we can iterate this inequality, so in each step we will get that u as k minus some mu k is less than equal as u as k minus 1 minus mu k minus 1 plus lower order terms. And using these inequalities, we can show that actually this mu k is a Cauchy sequence and it converges to a double convolution. And from here we can already obtain that ur minus mu, some double convolution u naught in the limit, is less than equal cr gamma u minus mu naught. And this holds for every gamma less than 1 and greater than 0. So this obviously already implies the uniqueness of blow-up limits and good decay estimates, which already will give us the regularity of the free boundary. So let me just draw one picture. Now if we think of a general case, and this is the limiting double convolution with straight lines. Now if we look locally at this point, and mu naught is the normal to this line, then we can see that, actually my picture is not so good, so we cannot really see it, but let me think that where we can scale more. Then we can see that our solution here to the obstacle problem is almost flat to this direction. And then we know that from the theory of the classical obstacle problem that flat solutions are flatness implies a C1 alpha for the classical obstacle problem. Furthermore, we can say that at this point we will have a unit normal vector, and we can estimate also the difference between this normal vector and the given one, which was the normal to the part to this line. We can even obtain this estimate, and from this we can already say that this piece of the free boundary is C1 alpha for every alpha less than 1. And then we see that the free boundary is a union of 4 C1 alpha curves. Yeah, and I have 5 minutes. That's good. I can talk about case 2. And what happens in case 2? So here this rotational argument doesn't work anymore because we have only finitely many blow-ups. But having finitely many blow-ups already gives us the uniqueness of blow-ups for free. Because if we just look at this function ER is UR minus mu1, where mu1 is one of the blow-ups, then this is a continuous function and it has a limit point 0. So if it had a limit point which is non-zero, then it would have any point between, which doesn't happen because we have only finitely many options. So the uniqueness of blow-ups we have for free, but also we may have the same, but then we can also look at this sequence Vj is uj minus mu1, and look uj, and to do the same argument. And then we get a function, but here, in this case too, we don't have right angles anymore. So here the expansion changes for V naught. So we get V naught something of this form. So it would be R alpha k k cosinus alpha k theta plus sinus alpha k theta, where alpha k is pi k over theta, I think. Just look it up to make sure that I'm not yes, pi k over theta. And it's easy to compute. But now when we see that here, in this case too, this angle theta is either less than pi half or greater than pi half. So if it's less than pi half, then the first term here will still have homogeneity greater than 2. So we still get flatness, we still get an inequality of this form, but with a worse power, depending on the angle. And in the other case, when theta is greater than pi half, we still have uniqueness of blow-up. So we can say, and from this we can conclude that the first coefficients have to vanish. And the second coefficients already give us the flatness improvement inequality of this form, depending on this, depending on the given data of the coefficients of the polynomials. And in this case as well, we can say that we have 4 C1 alpha curves meeting at a single point. Yeah. All right. So I think here we can stop the discussion on the two-dimensional case, and I will say about higher dimensions.
Are the energies different if you take this balanced energy? Are they different for different?
Yeah, actually, thank you for reminding me. I forgot to say about this. So when we have, we see that the solution depends on these angles.
Mm-hmm.
So when we have these double consolutions with the right angles, then the energy is the same for half space and for double consolutions.
Okay.
But when we have, when the angle is not pi half, then it already takes different values.
Yes. So it means because they are the same, it can rotate and you cannot control with only balanced energy.
So is the energy continuous in, with respect to theta? When the theta is not pi half?
I haven't really write it down and thought. I would guess so, but here I think I would rather go to see how it behaves with the coefficients, because the coefficients are different.
The problem is not stable, so maybe there
yeah,
is
because you know what's the problem, that we get 4 types of double consolutions, right? In case 2. So 2 of them have angle theta, and the other 2 of them have angle pi minus theta. So the angle is not fixed. We get the double consolutions with different angles.
Okay.
Yeah, so in R3, unfortunately, I don't have much to say, and I also don't have much time either. So, what we can say? First of all, we can say that we have polynomial solutions, and homogeneous global solutions. We have, of course, half-space solutions. Which are essentially one-dimensional. And we have two-dimensional solutions. And I will say what I mean with two-dimensional solutions. So two-dimensional solutions are the ones which are just translations of double consolutions to R3. So when we take obstacles which meet on a single line, then we can construct these solutions where the pre-boundary is a union of 4 half-planes. So something of this form, we can just think of this. We just have this kind of 4 half-planes meeting on a single line, which is exactly the line where the obstacle touches. So essentially that when we cut it, we see our double consolutions. And the question, if we have 2 3-dimensional solutions, We can say that yes, they are, because we can construct an explicit example where when we actually have the circular cones. So here u is equal minus r square, here u is equal r square, and this is the non-coincident set. But if this covers up the classification of blow-ups, or when do we exactly have each of these solutions, and what are the assumptions on the polynomials, are not known, so I cannot say much any further information on that.
Are there any questions?
Let's say if upper obstacle do not touch the lower obstacle, can we say that if it's large above a lot, then the solution only sees the lower obstacle? Or
Yeah, so that's what we saw in the beginning. So the point where the obstacles don't touch, locally we are at the center of the single obstacle problem.
then is there like uniform distance which separates the behavior?
Yeah, so we can just take a smaller ball so that the solution doesn't touch the other obstacle, and locally we are at that setting.
But I mean globally. Let's say you have two different obstacles, but they don't touch globally. And if the upper one is it's located too high above the lower one, can you say that the solution, the minimizer is just a minimizer for the single lower obstacle?
So you mean the distance between the boundaries? Yeah, it can be estimated.
Uh-huh. Okay.
Yes.
Yeah, so I was wondering, so for instance in R3, can you have different type of Riemann points that sort of converge to another of the time?
So I don't know.
No, okay.
So in 3 dimensions, all what I have done so far was just calculating symmetric solutions. But so the main question which I'm interested in R3 is, can we say that we always have circular cones? Because so in R2 we are in a very simple situation, because homogeneous degree 2 functions are polynomials, which is not true in R3, and it becomes much more. So under symmetry assumptions we can do the calculations. But
So what are the energies of this solution? Which are low energy, and how is can you rank them in energy?
you mean in 3D?
Yeah.
I haven't.
Okay.
Yeah, I haven't done it. Perhaps I haven't put it on.
In the linearization, what is the limit function? What kind of PDE does it solve?
Yeah, so here on the picture we have the graph, we have the picture of the given function mu naught to which our sequence is converging. And this one, the limit function, so it's harmonic in this non-coincidence part. So it's harmonic in this cone and it's in this cone, and it vanishes in this cone and in this cone, in the coincidence cones.
Oh.
So this is the.
Is there a Neumann condition or something? No?
No, we have it. It's a function only W1, 2, so we can say that it's only vanishing on these lines. We don't have.
Okay, in that case, should time is up.